My voice is audible?
Yes, sir.
Okay. So in yesterday's class, what we have seen, we were seeing about the feedback in state space, and we have seen that if we have a control canonical form, then we can. It will be much easier for us to calculate or to determine what is the feedback required, so that our pole should be in desired locations. Now, in yesterday's class, what we have discussed is there might be a condition, or there will be a condition when the given state space representation might not be in control canonical form, right? So for that, what we have to do, and so for that we have to use a transformation. A transformation to control canonical form only exists if the system is fully controllable. So if a system is given to you which is not in a control canonical form, but A, B, C, and D metrics are known to you, then you can calculate its transfer function, and then you can obtain its control canonical form from that. So instead of solving in non-control canonical form, it will be much easier for us to calculate the feedback required in controllable canonical form. Once we got the feedback required in control canonical form, then we can use a matrix which is transformation matrix, which is given by T. Then we will uh, make use of this T, and then we can get the feedback required for the original system which has been provided to us beforehand. So that was a concept that we have seen, and we have seen its derivative, and we will again see some of the algorithm steps that have been involved. For those who have not, for those who have joined late in yesterday's class, I will just recollect what we have covered in yesterday's class, and then we will see the example that we were already seeing in the last class. We will see what are the algorithms or the steps involved. Steps involved for getting the feedback required for a non-canonical form, right? So first step, that is step number 1, is find the transfer function. Find the transfer function. This is when you will do when the given system in your problem is not in control canonical form, and we have seen what is control canonical form. Control canonical form, suppose A, B, C matrix are there, and D matrix is also there. Where A matrix, you know that the top row has some elements, all the other rows are elements are either 1 or 0, like this, right? And B matrix is only one element is 1 and all the other elements are 0. C matrix is given by the numerator of the transfer function that you are having, and D matrix we have not seen, and we will not be considering D matrix. So this is our control canonical form representation. So we have to consider if given system, suppose if A matrix is provided to us which is not in control canonical form, suppose 1, 2, 3, and 4. This is our A matrix, and B matrix is 2 and 3, and we have to find we have to introduce a feedback here so that our pole should be in desired location. But right now we can see our system is not in control canonical form. So for such kind of a system, what are the steps involved we will be seeing here. Okay, so first what we will do is we will convert this system to a control canonical form. We will solve the feedback in control canonical form. We will obtain the value of K, and then by using transformation matrix we will find out K cap into T. We will use this formula, that is K is equal to, that is original, that is for this system we will call it as K, and k cap we will calculate for control canonical form, and T is a matrix which you will be calculating. We have seen in yesterday's class, T matrix is given by MCZ into MCX inverse. So these are the steps. We will see one by one what are the steps. So step one, for such condition when control canonical form is not given, is find the transfer function. And how you will find the transfer function? You already know the formula. It is ys upon us is equal to c si minus a inverse into b plus d. So this is the standard formula. You will use this formula, and from this you can get some amount of numerator, some numerator value and some denominator value, right? From here on, you know how to get the control canonical form. If you don't know, I will just explain. Suppose let us consider a random. From this step, if you're getting, I'm considering some random transfer function that you're getting as s cube plus 3s square plus 2s plus 1 upon s to the power 5 plus 4s square plus 4s4 plus 3s cube plus 2s square plus 9s plus 10. Suppose this is our transfer function that we are getting after solving from here. Okay, is my voice audible?
Yes, sir.
Okay, how to calculate the control canonical form of this? We can directly write A matrix. What is the order of the system?
5.
5. So A matrix will be of 5 cross 5. And what will be A matrix? What was the coefficient? It will be the negative coefficient in forward direction. So what is here is 4. So this is 4, sorry, minus 4, minus 3, minus 2, minus 9, and minus 10. And rest all the elements will be 1 and 0. So this is our A matrix, and B matrix is nothing but the first element is 1 and all the other elements are 0. And what is C matrix? C matrix is given by this positive coefficient in forward direction. Here you can see the coefficient of s to the power 4, the coefficient of s to the power 4 is 0. So we have to write 0 because it is how much? 1 cross 5 matrix. C matrix is 1 cross 5 because we are having 5. So first, that is s to the power 4 coefficient is 0. So I will write 0. Then we are having 1. Then we are having 3. Then we are having 2. Then we are having 1. So this will be our C matrix. So once you know the transfer function, you can get the control canonical form, right? So this is our first step. Second step, that is step number 2. Find the control canonical form. After the transfer function, you have to find the control canonical form, and we have seen that can be represented by z dot is equal to a cap z plus b cap u, right? Where a cap is what? We have seen a cap is a cap is E A T inverse, and B cap is T B. This we have seen, and if you are not aware of this, so I will again explain. So we have our standard state space representation. What is this? What is that? X dot is equal to AX plus BU, right? This was our standard equation, and we have used feedback where U is equal to minus KX. This was our feedback, and we said that we will again feedback to this. So X dot will be equal to AX plus B minus KX. So if you take BX common, so it will be A minus BK. And here you will be getting X. So X dot is equal to, this is our feedback equation, and we are calling it as a phi. Now, if so we will not be solving this, but we will be transforming this to a Z domain. Why? Because we know that solving in control canonical form is much easier for us. So first we will transform this in control canonical form. So for that we will be using transform, that is Z is equal to Tx. So X will be equal to what? T inverse of Z. Now substitute the values of X into this equation. So we will be getting T inverse Z dot is equal to A T inverse Z plus B U, right? So this is what we are getting. Now our feedback equation is u is equal to minus kx. Again, substitute the values of x in here, like we have done here. You can see from this. So this will be equal to u will be equal to minus k t inverse z. Substitute the value of this here, or you can call this as k cap also. You can call it as k cap z. So this will be equal to t inverse z will be equal to a t inverse z plus b, minus sign is there, minus k cap z, right? Multiply both side by t matrix. So this will be t into t inverse z is equal to e a t inverse z plus t into b minus k cap z. So this t inverse and t inverse will cancel out and it will be identity matrix. So this we will be getting as z dot will be equal to TAT. So TAT I am calling it as A cap Z plus TB I am calling it as B cap minus K cap Z. So if you take Z common, so this will be equal to A cap minus B cap K cap into Z dot. So this is our transformed equation. You can see here both of the equations are identical. Here this will be equal to 5. We have used the transform. So this is step number 2, is find the control canonical form. We will be seeing one example and then it will be much more clearer. Step number 3. Step number 3 is find the pole placement state feedback for control canonical form by using u is equal to minus a cap z. So we will use this equation and we will find the pole placement in state feedback. Now step number 4 is find the T matrix. T matrix is given by MCZ multiplied by MCX inverse, where MCZ is given by, we have seen MCZ is T into B, T into B, comma AB, comma A square B, up to whatever the order of the system is, A to the power n minus B, and MCX is equal to, is given by B dot cross AB, A square B, up to A to the power n minus 1 B. So first, from step number 4, you will calculate T matrix, and step number 5 is you will find the original feedback variables by using k is equal to, this is your original, k is equal to original feedback. You will calculate it by k cap into t. K cap you will be getting from this, and t you will be getting from step number 4. So that will be your feedback for the original system. So with this steps and algorithm, we will see one example. We have started that example in our last class. I will again repeat that. Question is, choose the k to set the closed loop pole at -1 and -1. So you have to select such values of k such that your closed loop pole should be at -1. There are two poles at the same location, that is -1 and -1. Okay, and A matrix is provided to you as -1, -2, 1, and -0.4, and B matrix is provided to you also 1 and -2, and C matrix is provided to you 3 and 4. So you can see here clearly A, B, and C are not in control canonical form, but still you have to set the value of k such that your pole should be at -1 and -1. Are you getting this question or not? Is my voice audible?
Yes, sir.
Okay, so you have to select such values of k such that your pole should be at -1 and -1 for this system. Okay, so how? But we have seen in previous classes that if given a control canonical form, you can directly calculate a minus bk, and if you calculate a minus bk, you will be having a matrix such that top row is having some elements and all the other elements are 1 and 0. But right now this is not in control canonical form, so first we will transfer, we will use the transfer function technique and the steps that we have seen in the above, and we will see how to solve this. So step number 1, find the transfer function. So we will find transfer function, that is ys upon us. What we are doing is we will find transfer function and we will find then its control canonical form. Transfer function will be given as c si minus a inverse into b plus d. So d here is 0, so it will be simply c si minus a inverse into b. So first we will find c si minus a. S is equal to, since it is a 2 cross 2 matrix, minus a matrix is -1, -2, 1 and minus 0.4. So if you solve this, so this will be equal to s plus 1 plus 2 minus 1 s plus 0.4. So this will be your s minus a matrix, and determinant of si minus a, we can calculate that also. But determinant will be s plus 1 into s plus 0.4 minus 2 into minus 1. So this will be equal to s square plus 1.4 s plus 2. Just let me know if I make any mistake. It will be 2.4 because you will be multiplying 1 into 0.4. It will be 0.4 plus 0.4, and here 2. Is it correct?
Yes, sir.
Okay. Now you have to find the adjoint of this. So adjoint of si minus a. So that will be given by just replace this diagonal element and multiply by -1 in the reverse diagonal element. So this will be s plus 0.4, s plus 1, minus 2, and plus 1. Now you have to take si minus a inverse. That will be equal to adjoint upon determinant. That will be equal to s plus 0.4 minus 2, 1, s plus 1 whole divided by s square plus 1.4 s plus 2.4. So this is si minus a. You have to multiply it by b matrix. So si minus a inverse into b matrix. So si minus a matrix is s plus 0.4 minus 2, 1, s plus 1 whole divided by s square plus 1.4 s plus 2.4. I'm just keeping it outside that is the determinant form, so that the mathematics can be much easier. And b matrix is given by 1 and minus 2. You can see here b matrix is 1 and minus 2. So we have to multiply that. So it will be equal to what? So how we multiply the matrix? The dimension is 2 cross 2 and its dimension is 2 cross 1. So finally we will be having 2 cross 1 matrix. We will be having a 2 cross 1 matrix whole divided by s square plus 1.4 s plus 2.4. And so first we will multiply. So this row will be multiplied by this column. So s plus 0.4, s plus 0.4 plus minus 2 into minus 2 is equal to plus 4. And second row multiplied by this column again. So 1 into 1 is 1 plus s plus 1 into minus 2. So if you solve this, so this will be equal to s plus 4.4. Just let me know if I make any mistake. s plus 4.4, and this will be equal to minus 2s minus 1 whole divided by s square plus 1.4s plus 2.4. Now you have to multiply with C matrix also, C into Si minus A inverse into B. So this is your Si minus A inverse into B. You have to multiply it by C matrix. And what is C matrix? That is C matrix is given by 3 and 4. You can see here. So this matrix is 3 and 4. So the dimension of this matrix is 1 cross 2, and dimension of this matrix is 2 cross 1. So finally you will be having 1 cross 1. So that will be equal to 3 into s plus 0.4.4 plus 4 into minus 2s minus 4 whole divided by s square plus 1.4s plus 0.4. So that will be equal to 3s plus, what is 44? 4.4 into 2 into 3. This will be equal to 12.
13.2.
13.2.
Plus, sorry, minus 8s minus 16. Is it correct? It is not 4, it is 1, I think. It is not 4, it is 1. Right? So here it will not be 16, here it will be 4 into minus 1 will be 4 upon s square plus 1.4s plus 2.4. So finally we will be getting as transfer function as ys upon us will be equal to c into si minus a inverse into b will be equal to 3s minus 8s will be equal to minus of 5s, right? 13.2 minus 4 will be equal to how much?
9.2.
9.2 upon s square plus 1.4s plus 2.4. So this will be your transfer function of the ABCD matrix. Now you have to obtain its control canonical form. Okay, so A matrix will be given by, if you want to write down its control canonical form, what will be the A matrix? It will be negative coefficient in the positive direction. What is the maximum order? You can see here 2 is the maximum order, so dimension will be 2 cross 2. So this will be equal to minus 1.4 and minus 2.4, and this row will be 1 and 0. So this is A matrix. B matrix will be, first element will be 1, next element will be 0. This is B matrix. And C matrix will be how much? Positive coefficient in reverse order. So minus 5 and 9.2. Any doubt in this part? We have got control canonical form from the transfer function. Okay, now we will find out, once we have got ABC and control canonical form, we will find out controllability matrix. Controllability matrix. And what is controllability matrix? That is MCX. We will find MCX and MCZ. Why we are finding MCX and MCZ? So that we can find transformation matrix, and transformation matrix will be given by MCZ multiplied by MCX whole inverse, right? So first we will find MCX and MCZ. So MCX is given by B comma AB comma A square B comma up to AN minus 1 into B. What is the order of the system? Order of the system is 2. So this part will be cancelled out. So MCX will be given by B comma AB. So B matrix is provided to you. B matrix is given by, in the problem, if you can see, B matrix is 1, 1, and minus 2. One and minus 2 is your B matrix, and AB matrix we have to multiply A and B matrix. So B matrix is 1 and minus 2 multiplied by A matrix. A matrix is, I think, minus 1 minus 2, 1 minus 0.4. This is a time-taking process, and its solution will be long. So keep patience. So minus 1 minus 2, 1 and minus 0.4. So you have to multiply this matrix. So this is 2 cross 2 matrix, and this is 2 cross 1 matrix. Finally, you will be having 2 cross 1 matrix. So rows multiplied by column. So minus 1 multiplied by plus 1 will be minus 1. Minus 2 multiplied by minus 2 will be plus 2. Sorry, plus 4. So this will be plus 4. Please let me know if I make any mistake. And second element is 1 into 1 is 1, plus minus 0.4 into minus 2 is plus, and 2 into 0.4 is 0.8. So that will be equal to minus 1 and plus 4 will be equal to 3 and 1.8. So this is AB matrix, and B matrix we already know. So MCX matrix will become B matrix, that is 1 minus 2, and AB matrix is 3, 1.8. So this is what we are getting as MCX matrix. Now we will calculate MCZ. MCZ matrix is given by B cap, comma A cap B cap, comma A cap square B, comma up to so and so forth, A cap n minus 1 B cap. So this is for control canonical form, and the order of the system is 2. So we will calculate up to 2 second order, and all the other elements will cancel out. So we will MCZ will be equal to B cap, comma A cap B cap, right? And B cap for control canonical form, you have already find out what is B cap matrix is 1 and 0, and what is A matrix. Now you have to find A cap and B cap. So A cap is how much? So this is your A cap, this is your B cap, this is your C cap. A cap matrix is minus 1.4 minus 2.4, minus 1.4 minus 2.4. Minus 1.4 minus 2.4, 1 and 0, and B matrix is 1, 0. So again, this is 2 cross 2 matrix, and this is 2 cross 1. Finally, you will be having 2 cross 1 matrix. So this will be equal to 2 cross 1 matrix. So minus 1.4 into 1, it will be minus 1.4, and 2.4 into 0 will be 0. Second row multiplied with this. So 1 into 1 will be 1. So this we will be getting as, so MCZ will be equal to B matrix, that is 1 and 0, and AB matrix, that is minus 1.4 and 1. So this is your MCZ. Now you can find out the T matrix as well from this point. T matrix is MCZ into MCX inverse, and MCZ is how much? 1, 0, minus 1.4 and 1, and inverse of MCX matrix is how much? This is our MCX, 1, 3, minus 2, 1.8. 1, 3, minus 2, 1.8. We have to find the inverse of this matrix. 1, 3, minus 2, and 1.8. Okay, so you have to find the T matrix. So for that, first you have to find the inverse of this matrix. So let me calculate the inverse. 1, 3, minus 2, and 1.8. Inverse. How will we calculate the inverse? That will be equal to adjoint upon determinant. What is the determinant of this? 1 into 1.8 minus 2 into 3. So that will be equal to how much? 1.8 minus minus plus 3 into 2, 6. That will be equal to 7.8. Is my voice is audible?
Yes, sir.
Okay. So first we have to calculate adjoint. Adjoint, how we will calculate? By by replacing the diagonal element and multiplying the reverse element by -1. So this will be equal to 1.8 and 1. I have reversed it and multiplied by -1, that is -3, and here it will be 2. Whole divided by determinant is 7.8. So this is our inverse matrix. You can see from here. I will not divide now. I will just calculate T matrix. So T matrix is how much? 1 minus 1.4, 1 minus 1.4, 0 and 1, 0 and 1. And what is the inverse matrix we have found out? 1.8 minus 3, 2 and 1 whole divided by 7.8. So we have to multiply both these matrices. So this is 2 cross 2, this is 2 cross 2. So T matrix will be equal to, final answer will be also 2 cross 2 and whole divided by 7.8. Let us just keep 7.8. At last we will divide. So for this element, this row multiplied by this column. So 1 point, just multiply it. 1 into 1.8 will be 1.8 minus 1.4 into 2 will be equal to how much? 14 into 2 is 28 minus 2.8, right? First row, second column. Now you have to multiply first row, second column. Just let me know if I make any mistake, okay? First row, second column. So 1 into minus 3 will be equal to how much? Minus 3 minus 1.4 into minus 1. This will be minus 1.4. Now we will multiply 0. That is second row. So it will be 0 only. And sorry, it will not be 0. 0 into 1.8 will be 0 and plus 1 into 2 will be 2. So here we will be having 2. And last row, that is second row and second column. So 0 into minus 3 will be 0 and 1 into 1 will be 1. So we will be having 1. So finally we will be having as minus 1 minus 4.4, 2 and 1 whole divided by 7.8. Just divide it and let me know the T matrix. Now divide by 7.8. Anyone? Minus 1 divided by 7.8 is how much?
Minus 0.128.
128. So let us write 0.13. And 4.4 divided by 7.8?
Minus 0.56.
Minus 0.56. 2 divided by 7.8?
0.256.
So let us say 0.26. And the last one, 1 divided by 7.8 will be equal to again 0.0. So this is your T matrix. We have calculated T matrix. Now you are having A matrix, that is A cap is given by, what is A cap? Where we calculate A cap? Minus 1.4 and minus 2.4. So minus 1.4 and minus 2.4, 1 and 0. This is A matrix, and B matrix is given by 1 and 0. Right? So this is A and B matrix, A cap and B cap matrix. Now you have to find pole at -1 and -1. So if pole is at -1 and -1, what it means, that is S plus 1 and S plus 1. If you multiply this, so this will be equal to S square plus 2S plus 1. Right? So this will be your equation according to which you have to find the pole location, S square plus 2S plus 1. Right? So here what you have to do is you have to find A cap minus B cap K cap. So you have to find A cap minus B cap K cap. Because K is your feedback. Right now the system is in open loop system. You can see here, and you want that your pole should be at -1 and -1. So now all the steps we have already seen, but so you have to find A cap and B cap and K cap. K cap is how much? K cap will be K1 cap, K2 cap. You can write it like this. So A cap is given by A cap minus B cap, K cap. So that will be equal to minus 1.4, minus 2.4, 1 and 0, minus B cap. B is 1, 0. So 1, 0 multiplied by K1 cap, K2 cap. Right? So this will be equal to minus 1.4, minus 2.4, 1 and 0, minus, now you multiplied this, so this the dimension of this is 2 cross 1, dimension of this is 1 cross 2. So finally you will be having 2 cross 2 matrix where you will be having K1 cap, K2 cap, right? And you will be having 0, 0 here. So if you do this, so this will be equal to minus 1.4 minus K1 cap, minus 2.4 minus K2 cap, and here you will be having 1 and 0. So this is A cap minus B cap, K cap. Now if you want to find out its determinant, what it will be, lambda to the power, what is the maximum dimension of this? You can see lambda square minus whatever the coefficient of this, that is minus 1.4 minus K cap, K1 cap into lambda minus 2.4 minus K2 cap into lambda to the power 0 is equal to 0. You have to compare this equation with the equation of s square, that is s square plus 2s plus 1, replace s by lambda. So we will be getting as lambda square plus 2 lambda plus 1, lambda to the power 0 is equal to 0. Compare the coefficient of equation 1 and 2 and calculate the value of K1 and K2. So let me do that also. So minus of this is minus minus, I'm cancelling it, so this will be equal to plus 1.4 plus K1 cap will be equal to 2, and 2.4 plus K2 cap will be equal to 1. So from here K1 you can calculate it as, what will be the value of K1? 1.4 will go to that side, so this will be equal to 0.6, and K2 will be equal to how much? Calculate the value of K2.
Minus 1.4.
Minus
1.4.
Okay. You can now substitute the value of K1 and K2 in A cap B cap matrix. So if you substitute here, 0.6, K1 is equal to 0.6, so this will be equal to 1.4 minus 0.6, that will be equal to minus 2. And if you substitute the value of K2 as minus 1.4, so minus 1.4 minus minus will be plus, and it will be having minus 1. So A cap B cap matrix is A cap minus B cap K cap, that is with feedback the matrix is coming out to be minus 2, minus 1, 1 and 0. And K matrix, that is K cap matrix, is given by 0.6, that is K1, and minus 1.4, that is K2. So this is K matrix. Now finally you have to find this feedback for your original equation, right? Original equation, this is the feedback for your controllable canonical form. But what you have to find out? You have to find out for original system, and what was your original system? If you can remember, this is our original system. This was our original system, right? So for this we have to find the value of K. You can see here we have to choose the K value, but right now we have got K cap, so we can directly get K value. If we get K cap, and we have also have transformation matrix, it's T, so we can use the formula K is equal to K cap into T. This is the formula that we will use. So T matrix is how much? Now you have to use T matrix. So this is your T matrix. Let me just copy it. So that will be equal to, this is T matrix. And what is K matrix? A is equal to K cap. K cap is how much? 0.6 and minus 1.4. This is your K cap, and the dimension of this is 1 cross 2. The dimension of this is 2 cross 2. Finally, you will be having the dimension of K will be equal to, what will be the dimension? 1 cross 2. So solve for this. So for this, this row multiplied by this column. So 0.6 multiplied by minus 0.13 plus minus 1.4 multiplied by 0.26. Calculate what it will be. Calculate this value. This will be your K1. 0.6 into 0.13 plus 1.4 into 0.26. Anyone?
3.7.
Minus?
3.72.
I'm getting minus 0.442. Have I made any mistake or you make any mistake? You have made any mistake. You have to solve.
Minus 0.442.
Yes, minus 0.442. Just check. It is coming minus 0.442. This is your K matrix, K1, and K2 will be equal to this row multiplied by this column. So this will be equal to, again, 0.6 multiplied by minus 0.56 plus minus 1.4 multiplied by 0.13. Calculate this. 0.6 into
Minus 0.518.
minus 0.518. So this is your final answer. This should be the value of K, so that your open loop state space representation should be. You should introduce this much amount of feedback, so that your poles are lying at -1 and -1. I will just recollect what we have covered. Okay, so let me go to the top. Okay, so here it is. Okay, so we have to find the value of K such that this state space representation, that is ABC matrix, should have pole at -1 and -1, right? So we have to solve for this. But when we have seen this, we came to know that this is not in control canonical form, so we cannot use directly by looking at A and B matrix. We cannot calculate value of K1 and K2. So for that, what we will do first, we will find its transfer function, and from that transfer function, we will obtain its control canonical form. You can see here, we are finding its transfer function by the formula C into Si minus A inverse plus B. And after doing some calculations, we calculated the transfer function. Though it is a lengthy solution, but finally you will get the solution. This is the transfer function. Now you have to calculate this controllable canonical form matrix, that is A matrix. So this is top row will be, you can see -1.4 and -2.4, and bottom will be 1 and 0, and B matrix will be 1 and all the other elements will be 0. C matrix will be the positive coefficient of the numerator in forward direction. So this is 5 and -5 and 9, 2. Next is to calculate T matrix, that is transformation matrix, and this will be given by MCZ into MCX inverse. So MCX will be original, that is originally what we have given, that is in X domain. Z is in transform domain. Okay, the control canonical form is in transform domain. So first we will calculate the controllability matrix for in original domain, that is X domain, that is B, comma AB, comma A square B up to A to the power n minus B. Right now, this is the second order, that is the order is 2, so we will calculate B and AB. So B matrix we can directly calculate, it is directly given in the problem, and AB matrix you have to multiply both of these matrices, and when you will multiply, you will be getting this kind of a matrix. Now you have to combine both B and AB matrix so that it can become an MCX matrix. So this is our MCX matrix. You can see MCZ, similarly MCZ matrix, you can find out B cap, E cap, B cap. And here B cap is control canonical form, that is B cap and A cap are control canonical form matrix. So B cap is in control canonical form. We know that B cap, only the first element is 1 and all the other elements are 0. Since this is the second order, we are having 2 elements. You can see, and A cap, B cap, we will multiply both A and B cap. So once we have multiplied, this is our matrix that we are getting A cap, B cap. So MCZ we have calculated that this is the value of MCZ. Now we will calculate T matrix, which is given by MCZ, that is in control canonical form multiplied by inverse of original form, that is controllability matrix. Right? So we have to calculate the inverse of this matrix. So for calculating the inverse of this matrix, we have done this adjoint upon determinant, and we have got this. Finally, we have got the transformation matrix, and this matrix is given by this matrix. You can see why we calculate transformation matrix, because by this we will calculate the how much feedback that is K required. So K will be equal to K cap into T. K cap is the feedback required in control canonical form. So we will calculate K cap. What is K cap? So A cap is given, that is control canonical form. B cap is given, and pole should be at -1 and -1. So we can form its characteristic equation, and it will be s square plus 2s plus 1. Why we have if it was -1 and +1, then we would have taken here s plus 1, s minus 1. That will be s square minus 1. Since the poles are at -1 and -1, so this will be our characteristic equation. Why we have done so that we have we can directly compare it with lambda equation. You can see we will calculate A cap minus B cap K cap. So K cap is K1 and K1 cap, K2 cap. Multiply this matrix, and finally we will compare this with s square plus 2s plus 1. You can see here we will compare both the coefficient, and such that K1 and K2 value can be known. You can see here K1 and K2 we are getting as this. So this is K1 and K2, you can see. And once you have got K1 and K2, you can use the formula K cap into T. T matrix we have already calculated. We multiply these. So this is our finally feedback required for the original system. Right? Any doubt in this part? Though it is a lengthy solution, but you have to be patient and